A portion of this video is brought to you by Surfshark.
Whoa.
Welcome to Jet.
Whoa. Oh my God.
Welcome to the Taurus Hall.
That is massive.
Getting to see the Jet tokamak fusion reactor in person was an eye-opening experience, but not in the way that you might expect. What I got to see during my time at the Culham Science Centre in the UK went well beyond what Jet is doing. There's a whole ecosystem that's needed to support a future fusion industry, and the UK government is really pushing every aspect of that. There's a lot of buzz around fusion startups, but for any of this to work, it's going to take a holistic view to address many of the challenges around it. So what's it going to take? And what's it like to stand inside of a tokamak? I'm Matt Ferrell. Welcome to Undecided. The old joke is that fusion energy is always 30 years away. However, it's long-running experiments like Jet that have helped to push our understanding of fusion forward and make major advances over the past few decades. Just a couple of years ago, it set the record for the longest sustained energy. Now, the whole reason I make these videos is to share my excitement and interest in technology and what humanity is capable of when we put our collective minds to a very difficult problem. Now, I'm not a scientist, so these videos are me sharing my learning journey and curiosity. And my journey over to the UK, which I've dubbed as my UK nuclear tour, is a part of that. Now, this is the first in a series of videos that I'm going to be releasing about that tour. You'll get to see everything from large government-funded research facilities to privately funded fusion to a small startup doing something with fusion that you might not expect. So be sure to subscribe and turn on the notifications to not miss those. Now, to kick things off in this video, I thought it would be a good idea to look at the big picture when it comes to fusion. And there's no better place to start than the UK Atomic Energy Authority, or the UK AEA, and the Culham Science Centre in Oxford. This really is a brain trust of brilliant people trying to tackle not just fusion energy, but everything that will be needed to support it. I'll be getting to Jet and the MastU tokamaks in a bit, but there's some interesting challenges that come with fusion. Just for a quick refresher, now when you're talking about nuclear power plants that we're all familiar with, it's nuclear fission, no U. That's when a neutron slams into a larger atom, which splits it into two smaller atoms. Now, additional neutrons are also released in this process and can start a chain reaction by slamming into more atoms to continue the process. When an atom is split, a massive amount of energy is released in the form of heat. Now, in nuclear reactors we have today around the world, that heat is captured to turn water into steam, which then turns a turbine to produce electricity. Fusion is the opposite of fission, and it's what's happening in our sun and all the stars in the universe. Fusion is when two atoms slam together to form a single larger atom. However, the single larger atom will be ever so slightly lighter than the two separate atoms. That extra mass is converted into energy. For instance, like two hydrogen atoms fusing together to form one helium atom. Now, the power released in this process is several times greater than the power released from fission. Once the fusion reaction is established in a reactor like a tokamak, a fuel is required to sustain it. There's a few different key fuels that are options for fusion. It's deuterium, tritium, or helium-3. Both deuterium and tritium are heavy isotopes of hydrogen. If you look at this graph, you'll see the output differences between deuterium plus helium-3, deuterium plus deuterium, and deuterium plus tritium. It's why most fusion reactors are eyeing deuterium plus tritium because of the larger potential energy output. Now, one important thing to keep in mind is that some of these reactions, like deuterium plus tritium, produce neutrons. And neutrons, unlike some other forms of ionizing radiation, can actually make things they impact radioactive. It's a process called neutron activation. And while the radiation generated by fusion reactions is short-lived, it's still something that you have to contend with and address, especially when maintaining a tokamak reactor. That's where my first stop at the Culham Science Centre comes into play and the solution I got to see. But before we get to that, I'd like to talk about another technology that I actually used during my trip to the UK, and that's from today's sponsor, Surfshark. I always recommend using a VPN when using public Wi-Fi, but VPNs can be very useful even when you're at home. A lot of online services use some pretty sophisticated commercial tracking and machine learning to apply very targeted advertising. A VPN can protect you from some of that. Surfshark's Clean Web does a great job blocking ads, trackers, and malicious websites, making it safer to use the internet even when at home. And you can even make it look like your IP address is coming from a completely different country. This can come in handy if you want to stream a video that's only available from a specific location. I actually did this on my trip in the UK. And one of the best parts of Surfshark is that it's easy to set up on all of your devices, whether that's iPhone or Android, Mac or PC. Surfshark is the only VPN to offer one account to use with an unlimited number of devices. Use my code to get 3 months for free. Surfshark offers a 30-day money-back guarantee, so there's no risk to try it out for yourself. The link's in the description below, and thanks to Surfshark and all of you for supporting the channel. Now back to that first stop at the Cullum Science Center. I had a chance to check the Remote Applications and Challenging Environments Facility, or RACE, which is all about creating mechanical systems to maintain dangerous or difficult to access machinery. Now one of the systems they've created is called Mascot, which is essentially acting as an extension of an operator's arms and hands. They can manipulate the remote gripper to remove panels, change out components, and do maintenance at a very safe distance. Now one of my first questions, which some of you are probably wondering too, was why this isn't a computer-controlled system? Why use a human operator at all?
So there is levels of automation in this. In terms of complete automation, given that it's one machine and we are, again, very delicate around everything we do, impact of delay is so huge, it's still being done manually and will through the life of this machine. Looking forward to other reactors in the future, there will be higher levels of automation in that, where they're going to be running for extended periods of time, have longer life durations, be doing more routine work. Where this is an experimental reactor, it's much more, you might do something just once. So the idea of programming an automated sequence for it, there isn't that huge value, but definitely going into future reactors is that you can retract the robot, pull the booms in and out, move them into position through automation, but when it comes to the actual handling of the environment,
that's when a human takes over.
Yeah.
As you can see from the monitors, they've created a digital twin of the reactor to work within for simulation, and to also give them multiple viewing angles of what's happening in the environment. Now, before an operator can even touch the real machine, it requires 1,000 hours of training time, which I actually got to experience for a few minutes. And to say it was fun would be an understatement.
This is a foot switch. If we hold this switch and push this button, the green button is on. That is force feedback it start to activate.
Okay.
You can also hit the table. You can feel the force feedback like this.
Okay.
Don't worry.
Oh, whoa. That is crazy.
Oh, that's a bingo.
Yeah, that is. Okay, this is the best video game ever made. That is so cool.
Let me fight you on that.
Yes. That is so awesome.
You could feel the edges of the block, or the right-hand gripper knocking into the left-hand gripper, as well as the weight of the block when you lifted it up off the table. It was pretty easy to see why these haptics are important for operation. Now, down on the floor of the facility, they have a massive work area of experiments with different technologies at play. And not to go down too much of a rabbit hole here, but in talking with the team, they explain why they're experimenting with mechanically driven robotics with things like gears and motors versus cables like Mascot uses.
So these are off-the-shelf two-handed manipulated robots that we are starting to work with and see what the value is of applying that kind of off-the-shelf technology.
Right.
Very different in the technology they use between them. This one is all mechanically driven throughout the whole thing with concentric shafts and gears, as opposed to a cable-driven system like the Mascot or the other off-the-shelf robot there. They have different benefits and drawbacks. The cable-driven ones are much more dexterous and feel a lot lighter things, but the mechanically driven ones are massively more radiation tolerant. The cables will wear quite heavily in high radiation impacts, whereas the mechanically driven nickel cells will last an awful lot longer.
When I got to try out this setup, it felt somewhat similar to the training system that I used, but I could feel the ticking and grinding of the gears as well. It took a minute to get used to that, but I don't mean to brag here, but I think I picked it up pretty quickly. It's surprising how quickly you adapt to the machine and get the basic hang of it. It looks like my lifetime of playing video games finally paid off, but even with that training, you still need something to test it on in the real world before you move into using it on the actual tokamak, which is why they have a life-size replica of the tokamak for the team to train on. I felt like a kid on Christmas morning, getting to go inside the tokamak and get a better sense for the size and scope of the device. And in case you didn't know, Jet is shaped like a giant donut, which shouldn't be too much of a surprise since the hint is right in the name, Joint European Torus.
So this is the inside of that torus. Apart from this section that I'm in right now, this is one of the actual octants off of Jet. So Jet is split into 8 segments, but there's actually 9, so the spare makes up part of the training facility.
Oh, okay. And when the mascots are used, this is where the training basically happens for them before you do stuff in the actual...
Yeah, precisely.
Forest.
So Mascot snakes in round here, and then we have the task module come from a separate opening. The task module is a table, but a fancy table, and the operators can basically practice all of the tasks that they need to do actually in the machine, because it's really important that the machine is turned back on as quickly as possible. So it's really important that the operators know what they're doing and they're really skilled at what they're doing, because dropping a bolt somewhere in here would be bad, but okay. But dropping a bolt inside Jet would be really bad.
While maintaining fusion reactors is a key part of RACE's research, it's not the only application of what they're doing. It has much broader applications for other industries that have hazardous materials or environments that might be difficult for humans to safely operate in. Now, we're looking into a potential future video on this topic, so let me know if you'd like to know more about robotics. Now, I've just scratched the surface of what I saw at RACE, but I was blown away by all the different experiments. This is an aspect of fusion energy that I hadn't thought about or even considered. My next stop was the newer MastU tokamak, where I got to speak to the director of tokamak science, Dr. Fulvio Melitello. And this ties right back to what I said in the beginning. The joke that fusion is always 30 years away is ignoring all the incredible progress that's been made over the past 40 to 50 years. Fulvio showed me the first working tokamak that was operated at the facility, and it was oddly cute.
This is a tokamak. This is an experiment that we had here on site working. It's not a model, it's the real thing at the end of the 1960s. And this is also to give you an idea of how much the field has evolved in 40, 50 years. Right. It's an incredible progress from a device that can literally sit on a table to what you probably see a Jet, or you will see a Jet later.
So things have evolved from small tabletop experiments to large-scale facilities. The MastU, which stands for Mega Amp Spherical Tokamak Upgrade Project, is important to the UK AEA because it's a major step towards achieving commercially viable fusion power plants that could provide clean, safe, and abundant energy. MastU is focused on solving the key challenge of plasma exhaust, which is needed to achieve commercial fusion power, and its new plasma exhaust system called SuperX has been designed to reduce heat and power loads, potentially making diverter components last longer. In my conversation with Fulvio, he mentioned that the diverter is key for commercial power plant designs down the road because of how it handles the excess heat that's not used for electricity generation.
What the diverter is fundamentally the handle of a cup full of hot coffee. So our plasma is the coffee that we want to drink. It's what we really want to get, right? We want to get this coffee as hot as possible, but we will not be able to handle it if we were just holding the cup with our hands. So we need a handle. And the diverter has the same function. It tries to separate this very hot and very energetic plasma from the surface of the device. Mm-hmm. And so we divert our plasma energy into this region of the device, here in the mockup, or up here and down here in this picture. And that component is specifically designed to accommodate these very large energy fluxes. Mm-hmm. This design that we have in Mastodon is unique in the world. Nobody else has it. It's called a SuperX configuration. Mm-hmm. It's just a technical term that we physicists use. But the idea is that it's specifically designed to accommodate this very large energy.
Yeah, I was very curious about the diverter. What made that? Because that's a very significant upgrade.
Yes,
from my understanding.
It is. And Mast Upgrade has already generated extremely interesting physics associated with this new feature. So, for example, we've been able to see that the energy that is coming out of the machine is very well handled by this new component. And the performance that we have observed compared to more standard designs are a factor 10 higher. So this is a really good result that we have already discussed with the scientific community. And we're very proud of it. And also in the new experiments that we're doing now, we will want to understand how our plasma is interacting with this new feature of the device. And we're very hopeful this design will become then part of future power plants.
The MastU's spherical tokamak design has the potential to be a cheaper and more efficient means of providing fusion energy than is currently possible in larger devices. As Fulvio mentioned, the new diverter reduces the heat of the exhaust material by a factor of 10, making it possible to channel the exhaust out of the machine at temperatures that the machine's components can withstand. That should increase the machine's lifespan and economic viability. But in the near term, MastU's whole purpose is to continue experiments and learning how this specific design handles plasma, increases energy output, and more. The ultimate goal is another big step towards power plants.
These experimental devices are not just for the physics, they are also to learn how to operate future power plants, how to maintain them, how to make sure that they are in the proper state, how to improve them. So there is also an important operational capability building that is done with these experimental devices.
Which brings us back to JET.
Whoa.
Welcome to Jet.
Whoa. Oh my God.
Welcome to the Taurus Hall.
That is massive.
This is my reaction when I did my thesis on a tokamak that was this big. And the first day I came here, I couldn't believe it was this big.
Oh my God.
I can count on one hand the number of times I've been blown away like that. One of my favorite moments was walking into the vehicle assembly building at NASA, where they built the Apollo rockets, and I got to see one of the space shuttles getting decommissioned. Now this ranks right up there, but that was Fernanda Ramini giving me the tour of JET. She's kind of a legend in fusion energy research and was instrumental in JET's recent record-breaking results. So it wasn't just getting to see JET in person that was awesome, it was getting to meet people like Fulvio and having Fernanda show me around JET that took it to the next level. JET has been around since the early 1980s and has gone through many upgrades and revisions over time. You can see some of that by the way it looks. It kind of looks like the house that Jack built. When I asked Fernanda how JET has stayed relevant for so long, I thought her answer tied in nicely to what Fulvio was hitting on too.
JET was designed and has always been operated with the physics and the engineering teams working together. So you don't just get physicists writing equations on the wall and engineers in a corner doing their work. There really is a dialogue between the two. And this allows the fact that, for example, when there is a physics breakthrough, like the H mode, that gives you plasma hotter, and JET wasn't quite prepared for that. But because of the engineering picked up on it, and so JET was changed significantly, and we could operate then in this H mode.
But it wasn't just the synergy between physicists and engineers that have kept JET relevant. There's another thing that's been taking the world by storm just this past year or two, and it's already been playing a role in fusion research, and that's AI.
Do you think AI is playing a big role in what feels like an acceleration of what we're learning?
AI is playing a big role. It will play a big role in the way we control the plasma and in the way we protect the plasma. We have solutions that come up on saying, oh, maybe we could implement this in our real-time systems from AI, and the physics teams is taking advantage of that.
So you can iterate through simulations quickly.
Yeah,
right?
We can iterate through simulations quickly. We can do simulations in real time as well. We can do model-based stuff in real time these days, which we couldn't even 10, 20 years ago.
That's just one example of why I think it feels like fusion research and startups are accelerating these days. I mean, there's a lot of factors, but computer modeling is dramatically accelerating research. Material science advances are addressing engineering challenges, like superconductors making smaller, stronger magnets. I've touched on that in a previous video about MIT's spin-off Commonwealth Fusion Systems. There's a lot of challenging issues getting resolved. As big and crazy as the JET tokamak looks, it's been an essential tool for the scientific community to learn about fusion reactor designs and how to control plasma and the reactions. They've added components over time to test different aspects of how things work and learn from it. But the part that kind of blew my mind was that they're also going to be learning from JET's decommissioning, which is going to be happening in about a year.
You can be learning from the decommissioning.
Oh yes, absolutely. The samples, for example, they will take samples from the tiles that are inside and analyze them to see what is the effect of the plasma being on them, how is the material, the tritium being implanted in the tiles, how are the material changed from the neutrons? How do we handle it? Can we handle it all with remote handling, or will at some point people need to go in?
I love that you're learning from every aspect of operating it, learning the skill sets of how to operate the machine, how to take care of it, how to take it down. I love
Yes.
that.
No, that will be absolutely, a first in terms of trying to learn as much as possible.
The UK Atomic Energy Authority is really taking a holistic approach towards fusion research. They have a new facility built that's currently looking into tritium research, which is a major sticking point for the future of fusion, and the fuel that most people find the most promising. As of right now, there's not enough tritium production in the world to support a commercial power plant, so that's another thing they have to figure out. They're also partnering with private companies to support varying approaches to fusion power. They have an incredible agnostic approach. I'll be talking about one of those companies in the next video, First Light Fusion, so be sure to subscribe and turn on notifications so you don't miss that. I was incredibly impressed with the size and scope of what the UK AEA is doing to support the broader fusion industry. I was even more impressed by all the amazing people I met there during my time. Thanks to Oliver, Leah, Fulvio, Fernanda, and everyone else I spoke to, this only scratched the surface of what I experienced, so I'm going to try to get more of this out on the Still to Be Determined podcast and over on my Patreon. So what do you think? Jump in the comments and let me know. And be sure to check out my follow-up podcast, Still Be Determined, where we'll be discussing some of your feedback. Thanks to all my patrons who get ad-free versions of every video, and thanks to all of you for watching. I'll see you in the next one.